Chemistry is the study of matter and the changes that matter undergoes. Matter itself is anything that has mass and occupies space. Literally, everything physical around you is matter. The most effective way to study chemistry is to follow the guidelines known as the scientific method. Initially, you gather data via observations and experiments. You identify patterns or trends in the collected data. You summarize their findings with a law, and you formulate a hypothesis. With time, a hypothesis may evolve into a theory, and at that point we can use the theory to predict outcomes of a situation. But of course, further experimentation can give alternate results, which will then modify the theory. Science is always adaptable, no matter what they say. Some things just happen to be more accurate than others. A great example of how the scientific method has developed something important can be seen in the development of the vaccine for smallpox. Smallpox was a virus that disfigured you and often killed you. It used to be a problem for millions of people. However, an observation was made. Milkmaids did not contract smallpox. A hypothesis was made that having contracted cowpox, a relative of smallpox, yet far less deadly, milkmaids had a natural immunity to smallpox. An experiment was devised based on this hypothesis. A healthy child, was intentionally exposed to cowpox and later to smallpox. Of course, this was at a different time when you could do experimentation on children. Let's not go there. Had the hypothesis been wrong, we would have had to revise it given the experimental results. However, because the child did not contract smallpox, immunity seemed to have resulted from the cowpox exposure, i.e. the hypothesis was deemed correct, and therefore it was stated to be a theory now. Now, further experimentation involved many more humans being given cowpox, and as they stopped getting smallpox, the theory was further confirmed and further cemented. However, had further experimentation shown that there was no relationship between the cowpox stopping or preventing the smallpox, then of course the theory would have been debunked. Luckily for us, it wasn't, and smallpox was eradicated by the 1980s. Due to the success of this vaccination, we then used the same method for multiple different viruses and have therefore been able to eradicate multiple diseases that used to kill millions of people worldwide each year. It's safe to say that the scientific method works, and it has some very good checks and balances in it to keep it adaptable. Scientific measurement. Properties that can be measured are called quantitative properties. A measured quantity must always include a unit. The English system has units such as the foot, the gallon, pound, and so on. The metric system includes units such as the meter, liter, kilogram, and so on. The US tends to like the English system, but the sciences are pretty much strictly in the metric system. SI base units. The revised metric system is called the International System of Units, abbreviated SI units, and was designed for universal use by scientists. There are 7 SI base units. Length is in meters, mass is in kilograms, time is in seconds, electric current is in amperes, temperature is in Kelvin, amount of substance is in moles, and luminous intensity is in candela. Become familiar with these and the symbols for each unit. The magnitude of a unit may be tailored to a particular application using prefixes. So instead of having a meter, you could have a centimeter, which would be 1/100th of a meter. You should become very familiar with all of these prefixes shown in this table and know their symbols. and of course to what number they correspond. Now you should be familiar with some of these already. Maybe you like to fiddle around with your computers and therefore you're familiar with terabytes, gigabytes, and megabytes, where megabytes means 1,000,000 bytes, gigabytes means 1,000,000,000 bytes, and terabytes means 1,000,000,000,000 bytes. Of course, these are very large numbers and therefore are less likely to come up in chemistry, where we're focusing on very small things. The common ones from the metric system are kilo, deci, and centi. So you may be familiar with the kilogram, which is 1,000 grams, and the centimeter, of course, 1/100th of a meter. Deciliters are a little less common, but they are used in Europe and they mean the 1/10th of a liter. We then have milli, which is 1,000th of something. So we know the 9mm bullet, that is 9,000ths of a meter in diameter. And if for some reason you're unfamiliar with the 9mm, you may be familiar with the 0.38, which is the same thing but in inches. Brr, we hate inches here. And then finally we get to micro, nano, and pico, where micro is a millionth of something, nano is a billionth of something, and pico is a millionth of something. These are very small units, but are very common in chemistry and biology and physics. Mass. Mass is a measure of the amount of matter in an object or sample. Because gravity varies from location to location, the weight of an object varies depending on where it is measured, but mass does not change. The SI base unit of mass is the kilogram, kg, but in chemistry, the smaller gram is often used, mainly because we do things on a smaller scale. So 1 kilogram is 1,000 grams, or 1 times 10 to 3 grams. However, an even smaller unit can also be used, which is the atomic mass unit. This expresses the masses of atoms and other similar-sized objects, where 1 atomic mass unit is 1.66 times 10 to the negative 24 grams, i.e. it's very small. That's 0.2400166, rounded down. Temperature. There are 2 temperature scales used in chemistry. The Celsius scale, where the freezing point of pure water is 0 Celsius and boiling point of pure water is 100 degrees Celsius, and everything relative to that scale. And then the Kelvin scale, which is the absolute scale. Here, the lowest possible temperature is 0 Kelvin, i.e. absolute 0. You cannot go lower than absolute 0. So if you ever see negative something Kelvin, you can guarantee yourself that the answer is wrong. Now this absolute 0 is at negative 273.15 degrees Celsius. This means that at 0 Celsius, we are at 273.15 Kelvin. This allows us to convert Kelvin and Celsius between themselves using this simple formula of Kelvin equals degrees Celsius plus 273.15. The Fahrenheit scale is common in the US. The freezing point of pure water is 32 Fahrenheit and the boiling point of pure water is 212 Fahrenheit. There are 180 degrees between freezing and boiling in Fahrenheit, but only 100 degrees in Celsius. The size of a degree on the Fahrenheit scale is only 9/5 of a degree on the Celsius scale. Due to this discrepancy in the scale, converting Fahrenheit to Celsius and Celsius to Fahrenheit actually requires this relatively complicated equation. To obtain a temperature in Fahrenheit, we must multiply the degrees Celsius by 9/5 and then add 32 degrees Fahrenheit to get the final answer. Derived units, volume and density. There are many units, such as volume, that require units not included in the base SI units. Derived SI units for volume is the meter cubed. A more practical unit for volume is the liter, which is 1 decimeter cubed, And as chemistry works on a much smaller scale, we're even more likely to use milliliters, which is 1 centimeter cubed. The density of a substance is the ratio of mass to volume. So density equals mass divided by volume. Learn this equation. However, the SI derived units is kilograms per cubic meter, and this is a large amount. So the common units based on states of matter are grams per centimeter cubed when you have a solid, grams per milliliter when you have a liquid, and grams per liter when you have gases. If you recognize the units, it becomes easier to figure out what state of matter, i.e. solid, liquid, or gas, the substance you are discussing is. Uncertainty in measurement. There are two types of numbers used in chemistry. We have exact numbers, are those that have defined values, i.e. 1 kilogram is exactly 1,000 grams. 1 dozen is exactly 12 objects. Or perhaps they are determined by counting, i.e. if there are 28 students in a class, there are exactly 28 students in a class. And then we have inexact numbers, measured by any method other than counting, i.e. length, mass, volume, time, speed, and so on. An inexact number must be reported so as to indicate its uncertainty. Therefore, significant figures must be used. Significant figures are the meaningful digits in a reported number. The last digit in a measured number is referred to as the uncertain digit. When using the top ruler to measure the memory card in this picture here, we could estimate 2.5 centimeters. We are certain about the 2, but we are not certain about the 5. The uncertainty is generally considered to be plus or minus 1 in the last digit. When using the bottom ruler on the image to the right, we might record 2.45 centimeters instead. Again, we estimate 1 or more digits than we are certain of. As a rule, estimate between the markings and the estimated digit is the uncertain digit. Significant figures. The number of significant figures, shown for sig fig, can be determined using the following guidelines. First, any non-zero digit is significant. So 112.1 has 4 significant figures. Secondly, zeros between non-zero digits are significant. So therefore, 305 still has 3 significant figures, or 50.08 is still 4 significant figures. Thirdly, zeros to the left of the first non-zero digit are not significant. So if we have 0.0023, we only have 2 significant figures, the 2, 3. Whilst 0.000001 only has 1 significant figure. Zeros to the right of the last non-zero digit are significant if a decimal is present. So if it is 1.200, it is 4 significant figures. However, if the zeros to the right of the last non-zero digit in a number that does not contain a decimal point may or may not be significant. So 100 is either 1, 2, or 3 significant figures, i.e. it's ambiguous. If we want to avoid ambiguity, we can use scientific notation to express the sig fig. So at 1 sig fig, it would be 1 times 10 to the power of 2, i.e. 100. Or 2 sig figs would be 1.0 times 10 to the 2. And at 3 sig figs, 1.00 times 10 to the 2. And honestly, the less ambiguity, the better. Calculations with measured numbers. In addition and subtraction, the answer cannot have more digits to the right of the decimal point than any of the original numbers. So if we add 102.50 with 2 digits after the decimal point to 0.231, which has 3 digits after the decimal point, we get the answer 102.731, but we should only report 2 digits after the decimal point, so the answer should be 102.73. We dropped the 1. Why? Because we cannot be more accurate than the least accurate number. Let's see it again. If we subtract 20.1 with one digit after the decimal point from 143.29, which has two digits after the decimal point, when we get the answer of 123.19, we can only state it to one decimal place, at which point we might as well round to 1.19 to 0.2 to give us 123.2. In multiplication and division, the number of significant figures in the final product or quotient is determined by the original number that has the smallest number of significant figures. So once again, we multiply 1.4 times 8.011. As 1.4 is only 2 sig figs, our final answer should only be in 2 sig figs. So even though the calculator will say 11.2154, we should report it as 11. Whilst in division, if we have this 11.57 divided by 305.88, the smallest sig fig is 4 sig fig. Therefore, when our calculator chugs out 0.0378252, we should report it to 4 sig fig, so 0.03783, rounding up. Exact numbers can be considered to have an infinite number of significant figures and do not limit the number of significant figures in a result. So for example, if we multiply 3 pennies, each having a mass of 2.5 grams, what is the total mass? Well, because we are multiplying by an exact number, the 3 has an infinite number of sig figs. So the smallest significant figures is the 2.5. Therefore, 3 times 2.5 can still be reported as 7.5. In calculations with multiple steps, round at the end of the calculation to reduce any rounding errors. So if the first digit to be dropped is less than 5, round down, so you drop. Or if the first digit to be dropped is bigger than 5, you round up and you add 1. But do not round after each step. We can compare the following. If we round after each step, we do 3.66 times 8.45 will give us 30.9. We multiply 30.9 by 2.11 to give us 65.2. If you round at the end, we do 3.66 times 8.45, we end up with 30.93. We do not round it, we keep 4 sig fig, even if we're not sure of that. And 30.93 times 2.11 will give us 65.3. And now we use sig fig and we get a different answer, but this will be a more correct answer. In general, keep at least one extra digit until the end of a multi-step calculation, i.e., don't worry about sig fig until the end. Accuracy and precision. Accuracy tells us how close a measurement is to the true value, whilst precision tells us how close a series of replicate measurements are to one another. Both are important in science, but I would say that precision is more important because you can correct for it. Just a visual though, good accuracy and good precision will always get your papers in the trash can. However, poor accuracy but good precision will always pile up your papers close to the trash can but not in it. This is my experience at least. And then poor accuracy and poor precision will just end up with your papers all over the place. As a more scientific example, here is a case study. 3 students were asked to find the mass of an aspirin tablet. The true mass of the tablet is 0.37 grams. Student A measured an initial mass of 0.335, a second mass of 0.331, and a third mass of 0.333. All these masses are very close together. They are precise, but they are not close to the true mass, i.e. they are not accurate. Student B measured 0.357, 0.375, and 0.338. These masses are all over the place, therefore they are not precise, nor are they accurate. And finally, student C measures 0.369, 0.373, and 0.371, which are all, with rounding, equal to the true mass. Therefore, his values are both precise and accurate. Using units and solving problems. A conversion factor is a fraction in which the same quantity is expressed one way in the numerator and another way in the denominator. For example, if 1 inch equals 2.54 centimeters, we may write it as 1 inch over 2.54 centimeters or 2.54 centimeters over 1 inch. You may have heard the term per. Well, 1 inch per 2.54 centimeters or 2.54 centimeters per 1 inch. We are just talking about a fraction or a conversion factor. The use of conversion factors in problem solving is called dimensional analysis or the factor label method. Example, convert 12.00 inches to centimeters. Well, we have 12.00 inches multiplied by our conversion factor. Well, which one do we use? Well, we want to use the one that will cancel out the current units and give us the units at the end. So as our answer is 30.48 centimeters, we should have the units centimeters on the top. And if we want to cancel out the inches, we need to be dividing by the inches. So in other words, we want to use this one. Notice that the result, 30.48 centimeters, contains 4 significant figures because the conversion, by definition, is exact. Now, if this stresses you out, just be aware that if you've ever counted money and figured out how much money you need to pay for something, you have been doing it all along. Don't overthink it. But feel free to come see me if you want to go over this more. Classification of matter. Chemists classify matter as either a substance or a mixture of substances. A substance is a form of matter that has definite composition and distinct properties. Examples including salt, sodium chloride, iron, water, mercury, carbon dioxide, and oxygen. Substances differ from one another in composition and may be identified by appearance, smell, taste, and other properties. A mixture is a physical combination of 2 or more substances. A homogeneous mixture is uniform throughout, also called a solution. Examples include seawater, apple juice, your coffee, etc. A heterogeneous mixture is not uniform throughout, and examples include trail mix, chicken noodle soup, etc. Matter can be classified as solid, liquid, or gas. Solid particles are held closely together in a ordered fashion. Liquid particles are close together but are not held rigidly in position and are fluid. And gas particles have significant separation from each other and move freely. Solids do not conform to the shape of their container. Liquids do conform to the shape of their container, and gases assume both the shape and volume of their container. All substances can, in principle, exist as a solid, liquid, or gas. We can convert a substance from one state to another without changing the identity of the substance. As you can see in this picture, we have boiling water heating up ice, which is frozen water, giving off steam, which is gaseous water. I.e., we can see water in both solid, liquid, and gas states. Yet the water itself, H2O, is exactly the same. A mixture can be separated by physical means into its components without changing the identities of the components. So for example, if you have some iron filings in sand, you can use a magnet to extract the iron filings, leaving the sand as sand and the iron filings as iron filings, without changing the chemical composition identity of either. Properties of matter. There are two general types of properties of matter. Quantitative properties are measured and expressed with a number, and qualitative properties do not require measurement, are usually based on observation. So for example, water in a liquid state, we could state that it is a liquid. That would be a qualitative property. And we could say we have 100 milliliters of it, which would be the amount of it, which is a quantitative property. A physical property is one that can be observed and measured without changing the identity of the substance, such as the color, melting point, or boiling point. A physical change is one in which the state of matter changes, but the identity of the matter does not change, i.e. the changes of state where we go from melting to freezing and condensation, etc. For example, when an ice cube melts, it becomes water after a physical change, but the chemical composition stays the same. Physical processes are things that we do to our substances. Examples of physical processes would be when mixtures are separated, but the identities of the matter do not change. For example, with coffee, when we pour hot water over ground coffee beans, we are extracting and physically separating the good stuff of the coffee with what we don't want from the coffee beans, but we are not chemically changing anything. A chemical property is the one a substance exhibits as it interacts with another substance. For example, it's the flammability or corrosiveness of the substance. A chemical change is one that results in a change of composition. The original substance no longer exists. So for example, digestion, combustion, and oxidation. If you take a cookie and eat it, it will not come out of you as a cookie. Just saying. Or maybe if you burn some charcoal on the grill, you're converting carbon into carbon dioxide. It becomes a gas, floats off. You are not left with the same substance. That would be a chemical change occurring. An extensive property depends on the amount of matter. So examples, mass and volume. Whilst an intensive property does not depend on the amount of matter, such as temperature and density.